and welcome back to quantum mechanics. Today, we'll be attempting to fully derive Bohr's equation for the hydrogen atom in one lecture. So, let's start with the radial equation, which is the basis we solved for the radial equation when trying to bring our Schrodinger equation from 1D to 3D, and then from Cartesian into spherical coordinates. So you have this plus, I believe, this is just going to be the potential function. And then you're going to have the centripetal term, which is over r squared. I can't remember the specific constants. Oh yeah. Are you kidding me? Is it just going to do that? So, this is equal to, this should be psi r, this should be psi r. So, this is Schrodinger's radial equation. Where do we proceed from here? You want me to close it? Where do we proceed from here? Well, the first order of business is to plug in the potential function, which for a hydrogen atom is going to be, well, usually it's kq squared over minus kq squared over r, which is minus q squared over 4 pi epsilon naught r. And in this case, since we're dealing with a hydrogen atom, the q in question is e, the one electron, which means that it's going to be minus e squared over 4 pi epsilon naught r, the unit charge. So, this gives us once dividing by E, the energy, plus minus E squared over 4 pi epsilon naught E R minus L times L plus 1 copper squared R squared. Psi r is equal to psi r. So now what's happening here? Well, first thing we can do is bring this over to the other side, or maybe we could bring this over to this side. So we get minus h bar squared over 2me psi r double prime plus minus e squared over 4 pi epsilon naught er minus L times L plus 1 over er squared. Are you kidding me?
Maybe you can use the notebook.
Now, is equal to 0 psi r. So now we can analyze the behavior of this function. I swear, that was a plus. We can analyze the behavior of this function as r approaches 0 and as r approaches infinity. Now, as r approaches 0, this is going to blow up, this is going to fall behind, and this is going to fall behind even more, which means we're going to get minus h bar squared over 2me psi r double prime is equal to L times L plus 1 over er squared psi r. Here we just do the standard guess, since psi r is probably a monomial, since its double derivative is 1 over r squared times some constant times the function itself. You can cancel out this, by the way, so it no longer depends on the energy. And you get psi r is equal to, let's call it ar to the something, k, and you get minus h bar squared over 2m k times k minus 1 is equal to L times L plus 1 psi r. I'm forgetting something. Definitely forgetting something. And so, at the end of the day, yeah, there's an extra factor of, yeah. Can't go back now. So this tells us that L is equal to K, since there's supposed to be an extra factor of minus h squared over 2m on this side. And you get that psi r around 0 locally acts like, what? R to the L plus 1. There's another solution, but it's going to blow up near 0. It's going to diverge since it's r to the minus L minus 1, and L is a positive integer. And, we want a wave function whose integral over the real line actually converges so that it means something. So, we get psi r is equal to a r to the L plus 1. Great. So, that's how it acts near r is equal to 0. Now, how does it act as r approaches infinity? Well, here, the reciprocal terms are going to go to 0 as their denominators will grow too large, while this term is going to stay constant, and so it's the only term that survives, and you get that minus h bar squared over 2me psi r double prime minus psi r is equal to 0. So you get that psi r is equal to, and now I'm going to do a quick substitution by letting rho be equal to, no, we're not going to do this. Yeah, this is the factor I was missing. Kappa be equal to square root of minus 2m e over h bar squared, and that tells us that psi r is equal to e to the kappa r. Actually, there were two solutions, e to the kappa r and e to the minus kappa r. This blows up as r approaches infinity, so we don't want it, which means we choose the one that goes to 0 as r approaches infinity, which means locally around 0, our function is going to act like a polynomial whose degree is dependent on L plus 1, and then it's slowly going to slow down or something. Nobody knows what happens here, but as it approaches infinity, it's going to look like an inverse exponential, which will slowly hover right above 0. So what does this middle behavior look like? Well, the only way to find out is by trying to isolate the asymptotic tails of the function. So, we get that psi r overline is equal to psi r r to the minus L minus 1 e to the minus kappa r, or plus kappa r, since we want to cancel it out. And so that means the other way around, psi r is equal to psi r overline r L plus 1 e to the minus kappa r. And so when you take a double derivative, this is going to become, well, first you have to take the single derivative because this is going to use the product rule. Overline prime multiplied by the r L plus 1 e to the minus kappa r, and let's let kappa r be equal to rho, because why not? And in fact, the amplitude from the other function can be absorbed in to the kappa to the n factor. So this is going to become e to the minus rho, which simplifies things a lot. And suddenly you get this plus psi r overline, the default function, multiplied by L plus 1 rho L e to the minus rho plus or minus e to the minus rho to the L plus 1, which means you can actually factorize this as rho to the L plus 1 e to the minus rho multiplied by psi r over line prime plus psi r over line L plus 1 over rho minus psi r over line. So there it is, that's the first derivative. And the second derivative is going to have to use the product rule again, to where we get psi r double prime is equal to what? Well, you get rho to the L plus 1, rho L plus 1 rho to the L, e to the minus rho minus e to the minus rho to the L plus 1. And that's just the side that has this with the derivative. L plus 1 minus rho over rho. And the other term is rho to the L plus 1 e to the minus rho times, what's the derivative of this? Well, it's psi r double prime plus psi r over line single prime times L plus 1 over rho minus 1 plus psi r over line multiplied by what happens when you take the derivative of this. Well, it becomes minus L plus 1 over rho squared. So this is the colossal form of the second derivative. Now what we're going to try to do is condense it by factorizing it. First thing we do is try to factorize rho to the L plus 1 e to the minus rho again, which will hopefully give us a simpler inner term. And so what happens here? Well, when you factorize rho to the L plus 1 e to the minus rho, you get this becomes L plus 1 over rho. This becomes minus 1. This stays the same as it does normally. Prime plus psi r over line L plus 1 over rho minus 1. Then you factorize this term and this just disappears, which leaves plus, so it just leaves all of this, which is just psi r over line double prime plus psi r over line single prime times L plus 1 over rho minus 1 plus psi r over line minus L plus 1 over rho squared. So now we simplify this even more by grouping up related terms, like we group up this and this to get what's hopefully the most condensed formation. Psi r double prime is equal to rho to the L plus 1 e to the minus rho multiplied by psi r double prime over line plus psi r 2 psi r over line prime. Remember, this is getting multiplied by that. Plus psi r over line times L plus 1 over rho minus 1 squared minus L plus 1 over rho squared. Okay, so this is the smallest that we can make the expression. And well, actually, we can go further by attempting to simplify this, but that'll come later. So now, what we're going to do is we're going to plug this back into the original spherical equation, where we had minus, I think, 1 over kappa squared psi r double prime. This is the thing that we're going to replace it with this. Trust the process. So you can actually rewrite this as over rho squared, L plus 1 minus rho squared minus L minus 1. And then this has to be equal to what? What's on the other side? Well, we're just going to bring that behemoth over there. So this is equal to this being, which we're going to abbreviate as, why don't we call rho naught is being equal to, let's try to get it simplified into some form, rho naught over rho. Remember that rho is equal to kappa r, and kappa is equal to the square root of minus 2me. All e's are negative, so this is a real number, divided by h bar. So now, how do we transform this into something that we want? Well, rho naught over rho is just going to be equal to rho naught over rho naught times the square root of naught minus 2me, rho naught times h bar over the square root of minus 2me r. So now we want to make sure that rho naught h bar over the square root of minus 2me is equal to all of this, minus e squared divided by 4 pi epsilon naught e. There's 3 different kinds of e's here. So you get rho naught is equal to minus e squared over 4 pi epsilon naught square root of e. Do not mind all of the evilness that's coming to this side. And this gets divided by h bar. There we go. That's rho naught. Which means that this gets condensed into rho naught over rho minus L times L plus 1 over ER squared. That is actually hard to deal with. So what are we going to do in this case? Well, we want to reduce it to something of the form, who knows, divided by rho squared. And rho squared is, of course, just kappa squared r squared, which means that this something or the other has to just be equal to L times L plus 1 times kappa squared, and kappa is the square root of minus 2me over h bar, which means this is just going to be times minus 2 me over h bar squared. So that means this is going to be what's on top. So you multiply this by that. So 2 me over h bar squared rho squared. Actually, no. There was already a factor of kappa on here from the beginning. Yeah, it was always, yeah, this was always just, yeah, that's an aspect of the equation that I totally forgot to write down from the beginning. That's why I wanted to restart. So, this multiplied by psi r, which is psi r over line, multiplied by rho L plus 1 e to the minus rho. First thing you might notice here is we can finally cancel out these parasitic factors, which means that we now get minus 1 over kappa squared. And actually, no, let's keep it this way. E to the minus rho. No, that doesn't exist anymore. Why did I put it there? Double prime plus 2 psi r over line single prime plus, now we're going to be forced to group these two together in a messy union. Oh, but how do I deal with the kappa squared factor? We'll get to that when we get to that, okay? So, let's see. Yeah, we'll get to that when we get to that. So, for right now, we have this plus psi r hat times this has a vacancy. So first, let's try to simplify this expression. What's L plus 1 minus rho squared? Well, that's just L squared plus 1 squared plus rho squared plus 2 times L times 1 plus, minus 2 times rho times 1 minus 2 times rho times L. So this is the entire expanded expression, and we subtract minus L minus 1, which means this disappears, and this gets cancelled. So you get L squared minus 2LP rho plus rho squared minus 2 rho plus L over rho squared. So I guess you can technically contract this, even though it doesn't help all that much. Blah, blah, blah. This is all stuff we've covered before. So now, going. Correctly? No, let's keep going anyway. So, we get that this is equal to, if we multiply both ends by minus kappa squared, this gets freed, and this gets put on the other side. Which means we now have to deal with that. And, what? Oh, okay. So, we get psi r over line double prime plus 2 psi r over line single prime plus psi r over line L minus rho squared minus 2 rho plus L over rho squared. And then we want to bring in this single term, but that's not going to work